the things. I've got a pointer. Yeah, great.
Yeah.
Okay, great. I got the camera on. This is on?
This is on, yeah.
Okay, great. Okay, thank you very much, everybody. And thank you to Marcus and Mauricio for inviting me. So what I'm going to talk to you about today, which I think is maybe a continuation somewhat on the theoretical concepts you've heard about this morning, regarding to, for example, neutrino oscillations. Here, I'm going to talk a bit more about kind of a practical example, an experimental example about how we actually go about measuring those neutrino oscillations in the particular case of the IceCube DeepCore detector. So I'm going to start with just a very brief overview of neutrino oscillations. So as I think probably most people in this room are probably familiar by now at this stage of the course, there are 3 neutrino flavor states. Maybe there are more stereo states, but in our current model at least, there are 3 neutrino flavor states, 1 for each of the lepton flavors. So an electron neutrino, a muon neutrino, and a tau neutrino. What is special about neutrinos, though, is that there is, in fact, these flavor states. So the states which interact in the weakened direction are not the same as the states that propagate, the mass states. There's a mixing between these flavor states and mass states. And this very special property of neutrinos gives rise to an awful lot of interesting phenomenology in new physics. This mixing tends to be characterized by the PMNS matrix. Now, the reason oscillations occur and what they are is that when a neutrino is created, it's created generally in a weakened direction and it's produced in a given flavor state. But because of this mixing, that really means it's produced a superposition of all 3 of these propagation states. Now, as the neutrino propagates through space and time, these 3 states all evolve together, their wave functions evolve. And because you have this superposition of states, you have an interference effect. And over time, this superposition changes and you have a time-dependent flavor composition of your neutrino, basically. And ultimately, what that means is the neutrino that is produced as one flavor, say a muon neutrino, has some probability at some point in the future of being detected as another flavor. And so flavor is not conserved here. And this is a pretty unique property amongst particle physics. Not too many cases of this are known. And this is what we mean by neutrino oscillations. Now, that was a lot of words. And I'll try and show the same sort of thing in a toy example in pictures. So we can try and take the simplest possible example of neutrino oscillation. So what I'm showing here is I'm imagining that there are only 2 neutrino states in the world, not 3 for simplicity. I'm calling them alpha and beta. You could just replace that with electron and muon if you prefer, or something like this, and 2 corresponding mass states. And I'm supposing that the mixing between these 2 is also basically the simplest thing possible. Each mass state is 50-50 mix of each flavor state. The other thing I'm assuming here is just that this relationship between the masses of the 2 states, which just gives basically twice the period of one of the other in terms of the wave function. And this is what the evolution of these states look like. So let's walk through this slightly. So this top panel here shows you your flavor states as a function of time or distance. Middle panel is the mass states as a function of time or distance. And then finally, we'll get to oscillations at the end here. So the very first thing that happens is your neutrino is produced in a weak interaction or decay in a single flavor state. So here you can see it's 100% in one flavor state, nu alpha here. Because of this mixing we already talked about, what this actually means, if you then look at this in the mass basis instead, you actually have both the orange and the purple here. So even though you're a pure flavor state, you're actually a superposition of 2 mass states. As the neutrino evolves over time, these are wave functions. You can describe these nice and simply as plane waves, and you have real and imaginary components. And these evolve over time, just like plane waves, with a frequency depending on the mass here, which I listed up here already. So basically, this is twice the frequency of one compared to the other. If we now look back to our flavor case over time, this evolution of your mass states produces this more complicated looking superposition in your flavor states. So you can see here already how your flavor composition is going to depend on time. And from an observational standpoint, what really matters here is then the oscillation probability. And what you can see here is that as you have this kind of complex evolution of your flavor states, you initially start with your 100% probability of detecting a neutrino in the state it's produced in. But over time, that will wax and wane, and you'll increasingly have the probability of detecting as another state. And then this will periodically move over time. This is a nice simple sine wave in a sort of a simple two state situation. So this is kind of a toy example of how oscillations really look if you break it down, not just the oscillations, but into the individual wave functions of the states that sort of underlie this process. So just a real quick recap of the basic neutrino oscillation phenomenology. I also already mentioned that that neutrino flavors are mixed with compared to the mass states here, and this mixing is characterized by a complex matrix, which is called the PMNS matrix. Now, if this matrix is unitary, which basically is the same thing as saying that this basically has a total probability of 1, or there are no additional neutrino states, then you can parameterize this matrix as 3 angles, typically called theta 1, 2, 1, 3, and 2, 3, and a single complex phase here. The other important parameters here are, I already showed you how the evolution of the mass states depends on the masses. But what really matters for oscillations is not the absolute masses, but the difference in the masses between the states, this interference effect. And so you have these 2 mass differences, basically the difference between the mass state 1 and mass state 2, and the difference between mass state 3 and mass state 1 here. And so you end up with essentially 6 parameters here to measure by experiment. And this is the core business of oscillation physics. Before you start going to more exotic BSM scenarios, the measurement of these 4 parameters is what the business of measuring neutrino oscillations really is. Now, just a little bit more on the phenomenology. So what do the oscillations actually look like? So again, going to the simple 2 flavor case, because writing this out in 3 flavors gets pretty complicated pretty quickly. The oscillation probability, so the probability to go from alpha flavor to beta flavor, depends on this mixing angle, which basically ends up being the amplitude of the oscillations. And separate then this mass splitting, which ends up defining the frequency of your oscillations. And for a given neutrino, this also depends on the distance it's traveled and its energy. So oscillations depend on these 2 fundamental parameters here, the mass splittings and mixing angles. And then for a given neutrino, it depends on their energy and how far they've traveled. So this is what the expression we're kind of measuring ultimately to extract these parameters. One kind of interesting piece of neutrino phenomenology is the case of the mass ordering. So what you might notice here is if you look at the mass splitting here, we're only dependent on it in terms of a sine square here. So we're not really sensitive to the sign of this. We only know its scale. And what that means is we actually don't know what is the heaviest neutrino. Is it the nu 3 or the nu 1 mass state? Or the nu 2, in fact, sorry, in this case. And this is one of the open questions in neutrino physics right now, trying to figure out this situation. And from this expression, you have no hope for it, but in a real situation with 3 flavors and matter effects, there are weak ways we can try and probe this, and I'll come back to this a little bit later. And the final bit of background on the phenomenology I want to mention is, and I think you've covered this a bit this morning, is that all these oscillation effects can be modified in the presence of matter. And so, for example, we have various matter effects like the MSW effect, parametric resonances, and then other related effects like absorption, tau and neutral current regeneration, etc. I won't be covering these in detail here, but these are things you may well hear about as you start to look at neutrino phenomenology in real systems with matter. And so I talked a little bit about what neutrino oscillations are, but we can always ask the question, why do we actually want to study these things? What is interesting about neutrino oscillations? And one of the most important reasons is because neutrino oscillations imply that neutrinos have mass. And in the standard model, in its most sort of traditional sense, the neutrinos are assumed to be massless. And so this is basically a concrete example of BSM physics. This is something we don't really understand how to theoretically explain. While these neutrinos, we do see they have mass, these masses are absolutely tiny, far below an electron volt, much smaller than any other known type of particle. And this gives us a question: why are these neutrinos so light? Is it because they get their mass from some other mechanism? Are there other complicated processes, like you might have heard of the seesaw mechanism? So we just don't know currently why neutrino masses, where they come from in general, and why they're so small. We can also ask questions about why do we measure the particular mixing angles we measure? Is it related to some particular symmetry, or is nature really just generated random numbers that we have to measure? Is there something more fundamental there? And why are the numbers, why is the mixing so different to the mixing we observe in the quark sector of the CKM matrix? A really big question is the question of CP symmetry violation. So I already showed you there was a CP violating phase, which was a view on neutrino oscillations. Now, we all know that we've all heard of the matter-antimatter asymmetry of the universe, and this is the fact that we basically live in a universe that's almost entirely made up of matter and not antimatter. And CP violation is a type of physics that can basically produce this difference between matter and antimatter. And maybe CP asymmetry in the early formation of the universe can perhaps explain why we see this universe today. But the CP violation we see currently in the quark sector is nowhere near enough to explain the current level of matter-antimatter asymmetry, and so maybe the neutrinos sector has something to say here. More generally, it's just a very rare opportunity to study a quantum system on a macroscopic scale. Quantum effects generally only perceived over microscopic scales, and they lose their coherence, and you cannot observe them over macroscopic scales. Neutrinos, because they travel so far without interacting with anything, because they only use the weak interaction, oscillations really are a quantum coherent effect at macroscopic scales, and there are very few real examples of that. You might have heard of examples of a quantum entanglement between ground stations and satellites of photons, for example. That's one of the only other ones that's really out there. So this is quite a unique opportunity as well. And the final motivation here is that oscillations are actually modified by a huge number of BSM theories. So things like stereo neutrinos, non-standard interactions, Lorentz invariance violation, quantum decoherence. All these situations, if they are real and out there in the universe, may actually make changes to the way neutrinos oscillate, and this is something we can search for in data. There are a number of ways to measure neutrino oscillations and to measure all the 6 parameters I showed you already, let alone more complicated BSM scenarios. We can't just use a single type of experiment. We need to see lots of different types of neutrinos over different energies, baselines, in different situations. There's a whole range of them here. So we have, for example, a number of accelerator experiments, such as those in Japan and the US. Nuclear reactors are a major part of a major source of neutrinos, and particularly for certain angles, so things like Diabei in China. Solar neutrinos are one of the original sources of neutrino oscillation physics. So this is the neutrinos produced in nuclear reactions in the sun's core, and leading to the solar neutrino problem observed in the SNO experiment. And then the last two here are the atmospheric neutrinos, which I'll talk about today, and astrophysical neutrinos, which I think you'll hear a lot about already today. This is not one of your more traditional oscillation experiments, but flavor triangle measurements still do constrain, for example, the mixing parameters. But I'll be focusing here on atmospheric neutrinos, and I'll explain a bit why now. When I'm talking about atmospheric neutrinos, right now I'm focusing particularly on the IceCube neutrino detector, but a lot of what I say will be general to other atmospheric neutrino detectors, other neutrino telescopes like KM3net or the BICAL experiment, or for example, the Super Kamiokande or Hyper-K experiments. But I'll be focusing a bit more specifically on IceCube here. IceCube, for those who don't know, is a detector at the geographic South Pole. It is located about 1.5 kilometers under the ice, and it is basically a lot of melted holes down into the ice with photomultiplier tubes lowered into position. And the real kind of USP of IceCube is that it's an extremely large detector. It's a cubic kilometer of ice, and because neutrinos interact so rarely, you need a very large volume detector to see them in high statistics. And because this detector uses a natural detection medium, hugely large than something like Super Kamiokande, it has the power to see very large numbers and very high energy neutrinos. The main detector is called IceCube, and this is around a gigaton total volume, and this detects TeV and PeV neutrinos. But actually, with what is maybe less well known is within the center of IceCube, there is this DeepCore subarray, which is a region where the PMTs are packed much more densely together, and this allows you to push down your energy threshold and start to actually study GeV neutrinos as well. And so IceCube was initially designed to study high-energy astrophysical neutrinos, but the background to those is the very large foreground, really, of atmospheric neutrinos. But what we actually now do is not just treat those as a background, but we actually use them for studies of particle physics and in particular oscillations. So a quick walkthrough of the phenomenology of atmospheric neutrinos in IceCube, but really in any experiment. So this is a picture of the Earth with IceCube down here at the South Pole. The Earth's atmosphere is constantly bombarded by cosmic rays from all directions, approximately isotropically. And when these cosmic rays, predominantly protons, hit the atmosphere, they produce hadronic showers of many mesons, hadrons produced, which then decay, and eventually you get a shower of muons and neutrinos. And so this is happening constantly all the time. And so there's what we really see is a constant beam of neutrinos being beamed down towards the Earth from the upper atmosphere. And we can exploit this beam with a detector like IceCube. This is dominated by muon neutrinos in most of the energy range we care about in IceCube here, but there's also an electron neutrino component, and then what's called a prompt component of charm decay here as well, of all flavors. But mostly it's muon neutrinos and some electron neutrinos. Now, once one of these neutrinos has been produced, it's neutrino, so not much gets in its way, and it can propagate all the way through the Earth here. And what this plot here is what we normally call an oscillogram. And what this shows you is a function of the neutrino energy and direction here, which is basically which is a proxy for its travel distance. This is the probability of a muon neutrino to still make it as a muon neutrino to the detector. And there are two main things to look at here. In this low energy region around 10 GeV and lower, you see these oscillation patterns here. So at low energies, order tens of GeV, we're seeing neutrino oscillations take place here for neutrinos that are traveling all the way through the Earth. The other thing you might notice here is this artifact at high energy here. And what happens here is that for the very high energy neutrinos, you actually have the neutrino cross section become so large that the neutrinos are actually absorbed by the Earth. They didn't make it all the way through the Earth. And so these neutrinos, you don't never actually see very high energy neutrinos coming up through the Earth. This is not an oscillation effect, but it's from a detector's point of view, it's still a lot of muon neutrinos. It looks a bit like here. And you can notice you've kind of got this blank area in the middle here where there is no oscillation or absorption, and there are no oscillations here because neutrinos of this energy need to travel a distance larger than the Earth's diameter to actually have any appreciable oscillation effects. So any oscillations you see here would be a very clear sign of BSM physics. And once these neutrinos ultimately make it to the detector, some fraction of them, a very small fraction of them, will interact in the detector. These undergo, for example, deep inelastic scattering interactions and produce charged secondary particles such as muons. These particles will move through the ice emitting Cherenkov radiation, and all our PMTs in the ice will observe this light. And we ultimately end up seeing something like this, a bunch of photons arriving at PMTs at a given time. This is ultimately what we see in the detector. In terms of IceCube DeepCore, this is a detector sensitive to the sort of roughly 5 to 100 GeV energy range. So you can see we're able to see this strong oscillation region here. This is probing of roughly the same oscillation parameters as long baseline experiments, but at a much higher energy. And so what we're really measuring here is this, what are normally called the atmospheric parameters. So this is θ2 and delta m squared 3 2. So to actually measure these effects, we need to basically measure all the dimensions on this plot. So we need to measure the neutrino energy. We need to measure the neutrino direction, which is a way we can then figure out how far it's traveled. And we also need to figure out, at least to some degree of fidelity, its flavor. And then when you put all those pieces together, these are all the pieces of your standard neutrino oscillation equation. And we can then derive the mass splitting and the mixing angle. In the detector, what we see is primarily deep inelastic scattering events. In this case, this means that either a W or a Z boson, depending on if it's a neutral or a charge current event, will penetrate into the nucleus and in fact even into the nucleons and interact directly with a quark. What typically happens at these energies is the nucleons completely break apart, and you have a shower of hadronic particles here, and lots of secondary showering and light comes from here. And then you'll also have a secondary lepton here, which depending on the flavor can be an electron, a muon, or a tau, or indeed just an outgoing muon that neutrino that you never see if it's a neutral current. At the low energy, so DeepCore energies order tens of GeV, the event signatures look like this. You might have seen IceCube event displays before, sort of huge cascades of PeV events or kilometer-long tracks in the ice. For tens of GeV oscillation physics, that's not what we're talking about here. The signals are a lot less clear. But what we really see is anything with an outgoing muon produces a track-like signature here. These are mostly charged current muon neutrino events, whereas more spherical emission is basically anything else, which is all the showering from all these particles, which are where the photons are scattering in the ice. So really, we're seeing track-like events versus cascade or spherical events. We actually have to reconstruct these parameters. How we actually do this is pretty complicated, and there are many different methods, so I won't go through this in detail. But broadly speaking, we use either machine learning or likelihood-based methods to reconstruct, to basically predict what a given particle's light deposition in the detector would look like, and compare that to what we actually observed to try to infer, for example, the particle direction or energy. We end up with, roughly speaking, around a 30% resolution on our neutrino energy and around a 10-degree precision in measuring its direction for these track-like events. The cascade events are harder to get the direction for because they don't have this nice long track to measure. Only the timing information gives us much, so we have a poorer resolution for these cascade events. And for the flavor, we're not particularly good at measuring the flavor in IceCube, but what we do is, as I mentioned already, we can try and identify this outgoing track from a muon. This basically tells us if an event was a muon neutrino event or not, and we have these these machine learning classification tools which try to predict whether an event was a muon neutrino or not. These are our free observables that go into the actual measurements. So how do we actually go about making this measurement? So what we're really fundamentally measuring is it's a particle physics experiment. It's basically a counting experiment where we're counting events as a function of energy or direction, etc., and comparing that to some model in simulations. We do this measurement in 3 dimensions, which is with respect to energy, direction, and flavor, essentially. Measuring in 3 dimensions rather than something like 1D, like you might do in a long baseline accelerator, is actually very powerful because it's very hard for systematic uncertainties to really mimic a full 3-dimensional oscillation effect. Whereas if you just have a dip like you would in a 1-dimensional accelerator experiment, then that's a bit easier for detector effects to mimic. So this is quite a robust method to build our expectation for what our data should look like, which we can then compare to what we truly observe. We first have to consider what the atmospheric neutrino flux looks like, and we do this based on satellite data for the cosmic ray spectrum and then hadronic models of how the evolution of the air showers develops. We then fold in our signal model, which is of course oscillations in this case. We then have to simulate how the neutrinos interact in the detector, which I've talked about a little bit already, and then finally we have to simulate the detector itself, so how the PMTs detect the light, how the readout electronics process that, etc., to give us a realistic example of what our data is going to look like. And ultimately, we then compare that expectation to data modulo nuisance parameters and estimates of our systematic certainties, etc. When you put all this together, you end up with something like this. So if you look at the true energy and direction of our particles coming in, this is what we expect we're seeing in IceCube right now with around 8 years of data. For our muon neutrinos, we have this pileup of events at the horizon. Most of the events we see at the horizon, you kind of get a geometric pileup at the horizon. But what we're really interested in is this upgoing region here at the bottom of the plot. So this is events coming up through the Earth. And here you can see a very clear deficit of muon neutrinos in these 2 bands here. And this is the oscillation signal we're looking for. If you look instead at our true simulations of the tau neutrinos, what you see is what we're observing is muons oscillating to taus. So the taus, you then see basically an appearance of taus in the same place where the muons disappeared from. Now, if this is what we were really seeing in the detector, this would be brilliant. We'd have an incredibly precise measurement. But of course, in reality, we have to reconstruct the properties, the energy, and the direction. And this has resolution. We're not too good in IceCube at doing this because it's a sparse detector. And so ultimately, what we end up seeing in the detector looks more like something like this. And you can see this is a little bit underwhelming compared to what you might have hoped for from there. However, even though it's nowhere near as clear a picture, we have very high statistics, so we're still able to measure this. And even by eye here, you can kind of see a deficit here in this region here, which is corresponding to where the muons are disappearing here. So there is still a signal here we can measure. And again, you still have this appearance then in upgoing cascade channel compared to the track channel here. There is still a measurement to be made, even if it's a bit underwhelming compared to what you see when you look at just your true simulations. Though it's worth noting that we are building an upgrade to the IceCube detector right now, which will have a far improved resolution. So it will be obviously not this good, but somewhere between these 2 pictures, and will give us a far higher fidelity measurements in the future. So that's basically how we do the measurements. So a few notes on the DeepCore oscillation program, and then I'll show you kind of our latest results. So the main strengths of DeepCore's oscillation program compared to something like accelerator experiments is mainly the high statistics. An accelerator experiment sees order a few tens, maybe 100 neutrinos across its oscillating in its entire lifetime. IceCube, our current measurements have hundreds of thousands of neutrinos, basically. So it's very high statistics compared to accelerator experiments, partly because the detector is very large and partly because there's a lot of atmospheric neutrinos. Secondly, we have very high energies. We have very large baselines. There's dense matter in the Earth. And so this provides sensitivity to a lot of different BSM oscillation scenarios. So as well as probing the standard oscillation model, IceCube is particularly good at searching for deviations from that and potential new physics scenarios. We mostly observe these deep inelastic scattering interactions I mentioned before. These are very theoretically simple compared to quasi-elastic and resonant cases at lower energies. And it's nice to make these measurements at energies different to accelerators where the theoretical uncertainties are very different. So if you get agreement between those two different types of experiments, it's very persuasive that you have the right model. The weaknesses on the other side of the coin are using natural ice as a detectable medium is not ideal. It's very hard to calibrate the ice properties, especially in huge volume. It's got dust, got layers from old ice ages or volcanic eruptions, this kind of thing. So it's not as easy for us to understand our detector as a purpose-built accelerator detector, for example. It's also very sparse. The PMTs in DeepCore are about 7.5 meters apart. Whereas if you think about a liquid argon TPC in June or something, I mean, it's got micron resolution. We've got nothing like that in IceCube at all. So resolution-wise, we cannot compete with a custom-built detector for an accelerator. Our power is the statistics and the high energy, basically. So they're very complementary. There are also it's also, although the atmospheric neutrino flux is nice, there's a lot of neutrinos and it's free, it's always on. It's also harder to understand than a dedicated accelerator where you really know exactly what your beam is. So there's theoretical uncertainties here. And as well as neutrinos, for every neutrino we see in the detector, we see millions upon millions of muons and other background. So background rejection is a big challenge in IceCube compared to most other experiments. The current generation of analyses we're working on, we use 9 years of data. And as I mentioned, this is around 210,000 neutrinos in that sample. This is the GeV scale. This is separate to a sample of around 300,000 neutrinos we have at the TeV scale that we use for BSM measurements like stereo neutrinos, for example. So overall, we have more than 500,000 neutrinos for probing oscillation physics across various scenarios in IceCube right now. And we continue to get more. You can see how we reject backgrounds here. So each of these stages is a stage where we do more and more background rejection for our data analysis. I won't go into this in detail, but what you can see here is your muons and your detector noise here are many orders of magnitude higher in rate at your low level detector data than your neutrinos are. But by using basically increasingly sophisticated methods over many layers of processing, we're able to really suppress these backgrounds to being subleading compared to our neutrinos. So many orders of magnitude of background suppression until we end up with a sample that is more than 99% neutrinos. And we also have very sophisticated models now of things like systematic uncertainties. Here, for example, you can see how the scattering in the ice changes a function of depth. And you can see all these complicated structures based on the kind of the glaciology and the atmospheric conditions over the last tens of thousands and hundreds of thousands of years. And we have to map all this out by basically using LEDs in our placed in the ice to try and map out these effects. There's a lot that goes into this. But given all that, we now have these models of our detector, of our systematic uncertainties. I've introduced you to the kind of what ultimately we're measuring, this kind of deformations of our energy and direction histograms. What do we ultimately measure? What you can see here is a summary of results from IceCube and other experiments in measuring these oscillation parameters. We're measuring two parameters here really on the x-axis. This is the mixing angle, basically, which you can just think of as the amplitude of these oscillations. And on the y-axis here, you can see the mass splitting, so the difference in masses. And this is basically the frequency of the oscillations. And what these contours show is, given our current results, anything within each of these contours is something that we favor as being the correct result within a 90% confidence interval. So what you really take away from this is that all these different experiments, some of these accelerators, some of these are atmospheric, some of these are IceCube, all these different results overlap pretty nicely. But this is even though they're taken across a wide range of experiment types and energies, this is really telling us that our current model of neutrino oscillations with free neutrinos, with no non-standard matter effects, anything like this, seems to be producing pretty consistent results across the whole kind of oscillation field as it stands, though there's still plenty of space and other anomalies out there we're seeing in other areas. The latest IceCube result was this orange curve here, using about 23,000 neutrinos, which is kind of a golden subsample of the nicest events, cleanest events. And we're now currently in the final stages of producing this red result here. So this red curve here is not result, but our anticipated result with the full 200,000 or so neutrinos that we were hoping to, well, we were actually hoping to do this summer, but we're a bit delayed. So in the next few months, hopefully this result will be finalized, and we expect to achieve something roughly comparable with the precision of the NOVA and T2K experiments here. Just a couple of brief notes of kind of a slightly less standard oscillation things we can do, or sort of additions to our oscillation measurements beyond just measuring the mixing angles and the mass splittings. The first is the tau neutrino appearance. So the main thing we're measuring in both long baseline accelerators and atmospheric neutrinos is muon to tau neutrino oscillations. But tau neutrinos are a slightly complicated case. The reason is, to detect these neutrinos, you need an interaction to happen. when you have a charge current interaction, you have to produce a lepton in the final state. However, the tau lepton is actually pretty heavy. It's more than the GeV in mass. And so if you're using GeV scale neutrinos, it's not actually easy to produce a tau lepton in your final state. What that really means is you need to actually have a neutrino at least 3.5 GeV in energy to even produce a tau neutrino interaction, and which you can kind of see here. And as you can see here, the cross section is really strongly suppressed, even to get up to sort of the TeV scale. So most accelerator experiments operate below 3.5 GeV or around that scale, and so they can't really see these tau neutrinos. When they're measuring muon to tau neutrino oscillations, what they're really doing is seeing muon neutrinos disappear. But they never actually see the tau neutrinos appear. It's inferred. That's what we believe the model does. One nice thing about measuring oscillations at high energies with something like IceCube is that because we're measuring at tens of GeV, we can actually see these tau neutrinos appear as well. And we can make a type of measurement that we call tau neutrino appearance. And the reason that's a particularly nice measurement is because if we really do see these tau neutrinos appearing when the muon neutrinos are disappearing, that really gives us confidence in our model of neutrino oscillations. And in particular, it tests an idea called the PMNS unitarity. And the idea here is that normally we talk about neutrino mixing as being a 3x3 matrix between the 3 states we know about. But I'm sure everyone here knows all about sterile neutrinos and the possibility, maybe we've seen them in some experiments, maybe we haven't, but no matter what you think about them, they're a well-motivated candidate for explaining why neutrinos have mass. Maybe there are additional neutrino states out there. And if there are, it's possible that some of those muon neutrinos disappearing in these accelerator experiments are actually going to sterile neutrinos and never being seen. They're not taus at all. So what we can do with something like IceCube is we test basically if the number of tau neutrinos we see seems to correspond with the loss of muon neutrinos. And if it does, then great, our neutrino model is good. And if we sort of see a deficit of tau neutrinos, then maybe that's an indication that some of those neutrinos are actually going to something else like sterile neutrinos, or there's something else wrong with our model. So the way we do this measurement, I sort of showed you this a bit before, but we do our standard oscillation result, but then we also separately add one extra degree of freedom where we allow our tau neutrino appearance rate to scale up or down as an extra free parameter. So a value of 1 in this normalization parameter would be the exact number of tau neutrinos we expect given the standard free neutrino mixing matrix. But if we detect less tau neutrinos than that, could indicate something very interesting. Or maybe if we detect more tau neutrinos, that would also be very interesting, and they're a bit harder to explain theoretically. IceCube, there are relatively comparable results from DeepCore, the Opera accelerator experiment, and the Super K atmospheric neutrino experiment before, but you can see these are all pretty large. All these results are roughly consistent with the standard expectation, but all have very large error bars because the tau neutrinos are still hard to detect even at high energy. But what the analysis we're working on right now, we actually do here at the Niels Bohr Institute, this is what we're anticipating doing by the end of this year, and this is about 11% precision. So this is much closer to the precision we have in the muon and the electron sector. And this is mainly just because we have so many tau neutrinos. We have about 9,700 currently in our IceCube data sample, and there have only been 200 tau neutrinos seen by all our experiments combined in the world, basically, previously. The final topic I'll very briefly mention here is the mass ordering. I already mentioned that there's this issue that we're not normally able to measure the sign of these mass splittings, only the absolute scale. And that means we don't know which is the heaviest neutrino. However, that is not 100% true. The reason is that atmospheric neutrino oscillations aren't happening in vacuum. They're passing through the Earth, and there are matter effects. And in particular, neutrinos that are of around the sort of 10 or maybe 8 GeV scale that pass through the Earth's core, it's a very dense region of matter. What happens is these oscillation bands, these aren't just simply bands here in this case. There's actually these distortion effects that are a result of the matter effects. And the reason this is interesting is because these effects only happen for neutrinos, but not antineutrinos if it's normal ordering, and it's the inverted case if it's inverted ordering. So if it's inverted ordering, this effect only happens for antineutrinos. And so if you're able to measure this effect, you can potentially try and understand which of these two cases is true in nature. Now, the problem with this is that DeepCore cannot tell the difference between neutrinos and antineutrinos on its own. It hasn't got a magnetic field to separate this. But the good news is that both the neutrino flux and cross-section is higher than the antineutrino flux and cross-section, which means that there are more neutrinos in our data sample than antineutrinos. So you still get a net effect of this, even without being able to distinguish them. It's very small. So with our current detector, we're only able to sort of probe this at the sort of 1 sigma level, which is very weak. But with the future IceCube upgrade detector coming later this decade, we expect to be able to make conclusive statements about measuring this signal. I think I'm a bit over time, so I'll just leave the summary up here. But I hope I've convinced you that neutrino oscillations are a very active field of research and something that really gets to the heart of trying to move beyond, really trying to understand what is next for particle physics, and really gets to the heart of some of the things we don't know about the standard model, I would say. And IceCube has got has a pretty powerful measurement potential in that area. Thank you.
Thank you, Tom. Are there questions? Yeah, let's start here.
Hello. First of all, I think it's really exciting that we can see this kind of precision in oscillation analysis and from this kind of experiment. So that's really, really good. I have 3 quick questions. First one, in the 2-dimensional posterior plots that you showed, is that assuming normal ordering or?
This one here?
Yeah.
Yes, this assumes a normal ordering. For us, it doesn't. The contrast doesn't change too much.
Okay. Okay.
But this is
And do you have any octant preference for theta 2-3? Because there it seems like it's exactly in the center, right?
We're very slightly in the higher octants.
Higher octant. Okay.
But your ability to prefer one or the other depends how close to maximal you are. And so since IceCube data has always preferred something very close to maximal, we also also means we're not really able to discern the octant either. Something like you can see here that the US accelerator experiments, Minos in blue here and Nova in purple, have always favored something a bit further from maximal, whereas IceCube, Super K, and TGK in Japan have always preferred something a bit closer to maximal, but they're all still pretty compatible within the precision. Fair,
fair. And then the oscillogram you were showing earlier. Yeah, so I see quite a big break there. Are you using, how many layers are you using for the Earth modeling? Is it like a prem or is it just 2 layers?
This is a prem. I forget how many we're using this. I think it was 60, but I forget exactly how many. I think we've done studies in the past to figure out how many really matter. We do end up with a little bit of a transition around the Earth's core there, but at the same time, there is actually a relatively sudden transition when you go from the inner core to the outer core. It is a relatively fast on this scale. Bear in mind that when you break this angle up, you'd be still talking about fairly large distance scales. Yeah.
All right. Thank you.
This is the preliminary reference Earth model.
Okay. Yeah. Thank you.
Thank you for the talk. So for detecting towers, you look for like the double cascade, right?
Actually, just to clarify, for the question was for detecting the tau neutrinos, we're looking for double cascades. Actually, for what I've shown here, that's not the case.
Okay, right.
So the double cascade, for people who don't know, is the idea here is that when you have the interaction, the nucleus breaks up and you have a cascade. The tau neutrino then travels a little bit and then decays, and you get the second cascade. Now that double cascade signature is useful for probing tau neutrinos at hundreds of GeV. Right. Because at that point, the time dilation is such that the path length can be meters for the tau before it decays. At GeV scales, you're still talking millimeters for the path length, and so we don't directly see the towers exactly. What we really see is an excess of cascades with their cross section suppressed, as we think it should be from the mass of the tau lepton appearing where the muons disappear. So it's that's kind of the opposite from something like the opera experiment, where they could really see towers by using motion film. So they are very confident in seeing a handful of tau neutrinos, whereas we statistically see many, but for no individual event we can 100% say that's a tau.
Okay. So can you still get directional information from the towers?
We can. It's around 30 degrees precision, something like that, at this sort of 10 GeV scale, something like this.
Oh, cool.
Yeah.
Thank you.
So 60 times the moon.
Yeah.
So 30 degrees.
Yeah, hi, thanks so much for this talk. You mentioned these distortion effects because the neutrino oscillations don't happen in the vacuum, but in the atmosphere and also in the Earth. Yeah. We learned before about these coherent forward scattering effects, but those take place in much more dense matter, right? Or is this also?
These are actually coherent forward scattering effects as well. So I mean, in the dense case, like for example, the supernova case, I mean, they're extremely strong effects. But for crossing the Earth's core, you can still pick up, at the right energy, you can still pick up coherent forward scattering. And so these signals here, these signals here are actually a combination of parametric resonances and MSW resonances, and both of those are the result of coherent forward elastic scattering with electrons.
Ah, so this is really the reason.
Yes, that's right.
Okay, thanks.
One quick last question.
Yeah, it will be very quick. Maybe it may sound more like stupid, but can you please go back to slide 35? And there, you have mentioned in the y-axis about the signal to background ratio, is it?
Yes, that's right.
And
yes.
what exactly is your signal to background noise ratio?
Sure. So this is an attempt to kind of visualize what the tau neutrino signal is. And so what this color, the z-axis here is signal here means number of tau neutrinos, and B background means number of every other type of event.
And why are you taking a root over it?
This is just a traditional method for basically quantifying significance. So what you're really saying is the square root of the background is really telling you the statistical uncertainty on your background of the count, your background counts in each bin. And so what this is essentially a measure of significance. So it's how many events do I see divided by the uncertainty on the background events.
But if there would be no root, then will it amplify your ratio?
Sorry?
If there will be no root over it, then will it amplify your ratio?
It would be, so if you drop the square root, the denominator would go lower here, and that would reduce the size of your signal. But it's worth pointing out this is not actually used in the measurement. This is just kind of a way to try and visualize the signal.
Right.
But the actual measurement is a full Poisson likelihood measurement of the comparison of the data.
So do you do a negative log likelihood test, or how? For the Poisson negative log likelihood
Yes,
test?
exactly.
Okay.
It's a negative log likelihood comparison of the histogram we see of the data events in 3 dimensions compared to the simulated expectation with our models. It's forward-folded parameter estimation, basically. It's a negative log likelihood optimization where the likelihood is defined such as a Poisson likelihood, which are defined for Poisson counts, and then we have a term, an additional term, which is a penalty term for the Monte Carlo statistics. Basically.
Thank you.
Yeah.
Okay, we have to move on. Thank you very much, Tom, for this very nice talk.